Okay, in this video, in this lecture, we're going to cover section 5.5, and this will be the end of chapter 5. And this is on inverse trig functions and their graphs. Let me share my screen. Five 5.5 inverse functions and their graphs. So it's not the case that if you consider any one of the trig functions on its entire domain that it's going to be invertible. It's going to be injective or one-to-one. And this is precisely because these functions are periodic. Remember, their values repeat. So they're, in a sense, these functions fail to be injective very strongly. Any given output is the value of infinitely many distinct inputs, right? So, for example, sine x has a value. It has a period of 2 pi. So what that means is that if I take sine of x plus 2 pi n, that's going to be sine of x. If I say I just fix x and I just look at n varying, so this equation holds for all integers n. So for each n, so each value of n gives a distinct number x plus 2 pi n. So if you take different values of n, this number will be different. There'll be an infinite number of distinct numbers. It's a whole family of numbers. And this says that all of those, when you take sine of all these numbers, it just ends up being sine of x. So, and we're thinking of x as some fixed number. You fix a number x, and then you look at all these values, and they all end up equaling sine of x. So it fails to be injective very strongly. But it's the case that if you restrict the domain of sine, then you can actually define an inverse function. And we've kind of seen this already. So if I take the function f, which goes from r to r, so the domain is all real numbers, and I define it as this, the function on this domain is definitely not injective, because f of -1 is equal to -1 squared, which is equal to 1, and that's 1 squared, which is equal to f of 1. So -1 and 1 are different, but they give the same outputs. So when you're thinking about injectivity of functions, or whether it's invertible, it's not just the rule that you have to look at. You also have to look at the domain. But if you were to redefine f, if you were to redefine the domain of f to be all non-negative numbers, so from 0 to infinity, including 0, so what this says is not injective. And actually, let me use a different symbol here. So if you redefine it, so I take g, and then I take g of x to be x squared, then this is injective. And therefore, it's invertible onto its image. In fact, its inverse is the square root function. So this function is invertible. So when you think about, when you look at a function on a different domain, it might, when you look at, so the idea is you have these rules. A function consists of a domain, a codomain, and a rule for assigning numbers between, or elements more generally, between the domain and the codomain. So you have these three pieces of information that go into make a function. Now, if you change the say the domain, it's possible that that rule now becomes a one that's invertible, that you can reverse the rule in a sense. And that's going to be true for trig functions in the way that it's true for this function right here, x squared. So the reason why this, basically the rough idea is the reason why x squared fails to be invertible or injective or one-to-one on R, the whole real line, is because when you take the square root, you have to worry about positive and negative roots. But over here, when you redefine it on this domain, you don't have to worry about that. You always have to take the positive root, so it's unique. You don't have to worry about, well, do I take positive or negative root? You always take the positive root. So let's look at, I'm going to pull the book open and we'll look at the graph, which we've already seen. We'll look at the graph of sine x. And of course, this whole discussion right here, right here on the sine function applies to the cosine function, because again, the cosine function has a period of 2 pi, and you can also do the same sort of analysis on tan, cotangent, secant, cosecant, to show that none of these functions are injective, none of them. But I guess it's going to turn out that they're nice enough that we can restrict them, restrict their domain to get an injective function. So let's look at the graph of sine of x. So sine of x looks like this, and we always think about plotting it from 0 to 2 pi. So this one, it goes through the origin, but the difference between that and cosine is that the cosine starts at 1 and goes down. So this one starts at 0, goes through the origin, goes up. But if you look at the function, so we're looking at the function from negative pi over 2 to pi over 2. If you just, this red segment right here, if you were just to chop all that off like we do over here, notice the function satisfies the horizontal line test. So on this domain, the function satisfies the horizontal line test. Obviously, it does not satisfy the horizontal line test on the whole real line, because if I just draw a line here, see, there's one value here, it intersects, one value here, one value here, and then it just goes off infinitely many times. Oh, so sorry, there's some values here and here. So there are infinitely many points of intersection. That was the whole point of this period, the function. That's what I was mentioning earlier about the function being periodic. It takes on any given value infinitely many times. Any given value between 1 and negative 1, because these functions don't go above 1. It doesn't go above 1 or it doesn't go below negative 1, but any value between 1 and negative 1, it takes on that value infinitely many times for infinitely many distinct numbers. But here it's clear that it satisfies the horizontal line test and is therefore invertible. So we can summarize this as follows. So this is the inverse sine function. So the inverse sine function is the function sine negative, and I'll just put empty parentheses here to indicate that that's where it takes in its values, and it's a function from -1 to 1 to negative pi over 2 to pi over 2, defined by, and this shouldn't be, again, none of this should be mysterious, because this is just basically by definition what it means to be invertible. This is how we define, if you go back and you look at the definition, the general definition of an invertible function, this is just the definition applied to the sine function. So it's given by this: sine inverse of x is equal to y if and only if sine y is equal to x. So again, a function is a domain, codomain, and a rule. And what this says is that the sine inverse rule is defined in terms of the sine function rule. So what you do is to find out what it does to a given x value, you call that output value y, and then you just look at what sine does to y. And so it's sine inverse sends x to y if and only if sine sends y to x. So, and this is how we get that cancellation property, remember? So I want to point out one thing. So first of all, sine inverse also, sometimes it's denoted by arcsine. And again, I'm using these empty parentheses to indicate the fact that this is where the input is. See, this is where you plug the numbers in. It's just like if I wrote this, it's just an empty symbol, and that's where the inputs go. I'm not really saying what the input it looks like. I'm not saying it's X, Y, Z, whatever. So this is also denoted by that. So first of all, I just want to point out that sine. So remember, I use this convention right here, sine squared of x. I define that to be sine of x squared. So that was just convention, nothing mysterious there. This is where the convention kind of breaks. When I write this, I do not mean this. It's not the reciprocal, it's the inverse. So inverse does not equal reciprocal. I think I spelled that right. I don't know. Maybe not. Anyways, this is not true right here. That's not true. So the idea is, again, let me just go through this really quickly. We restrict domain of sine, and what we restrict it to is this. And remember, sine, in maybe the video or two ago, we proved that sine and cosine are bounded between 1 and -1. So every output value lies between -1 and 1. So this is the domain, this is the codomain, and in fact, this is the image. The image equals the codomain in this case. I mean, you can always just restrict the codomain to be the image. That's really the easiest thing to do. But if that's the case, this implies, remember, one part of the definition of inverse function is that the inverse function has the domain and codomain swapped. So that's why sine inverse goes from -1 to 1. Or from -1, 1 to negative pi over 2 to negative 2 pi over 2. And of course, we have some, as I said, inverse functions have a cancellation property. And so this is, again, this is all just by definition. So if you just carefully look at those definitions of what it means to be an inverse function, and if you look at the definitions of sine and cosine, this shouldn't be terribly mysterious. So these are the cancellation properties that we have. And these follow by definition. They follow from the definition of what it means to be an inverse function. And it should look familiar. The idea is that if I take sine of sine inverse of x, that better be x, because they cancel each other out, remember. And this is for any x between 1 and -1. Because remember, the only numbers I can plug in a sine inverse are between 1 and -1. So x better be between 1 and -1. So this identity, this equation holds, this equation right here holds when x is between 1 and -1. And then I have the other cancellation property, which says that if I take sine inverse of sine x, that better be x. As that's just what it means for, that's just what it means for sine inverse, this thing right here, to be in the inverse function of sine x. And this only makes sense for when x is between negative pi over 2 and pi over 2. So remember the graph, let's look at the graph again. The graph, if you remember, graph of the inverse function is basically you take the graph of the function and reflect it about that diagonal line. So here, so we're thinking about inverse, what sine x and restricted to negative pi over 2, pi over 2. So that's what the plot looks like. And then you have, I'll try my best to do this, but you have this diagonal line here. It's kind of, I don't know why this, I don't know how to change the size of this. But anyways, wait, maybe I can do this. Yeah, okay. Something like that. So you have this diagonal line and it sort of intersects here. And then you're just going to reflect over that line. And what you're going to get is this right here. This is the inverse function right here. The graph of it. So let's, we've been talking very abstractly and generally. Let's look at some examples. So this is, we'll do some computations to get used to just to get used to what inverse functions again, because we haven't looked at these in a while. Just to get used to the definition of inverse function, and then also the definitions of the trig functions. So this is example 1 in the book, part A, and we're asked to compute sine inverse of 1/2. Notice 1/2 is in the domain, so it makes sense to ask what is sine inverse of this, because 1/2 is between -1 and 1. Well, what I like to do is I like to say, okay, we'll call this y, and then I'm gonna apply sine to both sides. So if I apply sine to both sides of the equation, I get this, and then it changes the question a little bit. It says, the question becomes what number, so what number between pi over 2 and negative pi over 2 and pi over 2 gives me this? What number do I need to like what's the, I mean, we haven't talked about angles really, but what's the angle between these two that gives me one half? And remember, the sine takes out the, it's defined as the, this is actually confusing because I'm using y. Let me not use y, let me use theta. So remember, if I give you a number theta or t as we have been using, that gives you a point on the unit circle, and then sine plucks out the y coordinate. So the y, we're saying that the y coordinate, I give you some number t, and we're told that the y coordinate is 1/2. And the points are coming from the first and the second quadrant. So let me draw the unit circle. So when you're, that's the best I can do. So here's the reference point right here. This is 1, 0. And all these values here correspond to points here, stopping here, and here, stopping here. So here's pi over 2, which corresponds to 0, 1. And then this is negative pi over 2. Oops. Which corresponds to 0, negative 1. So I'm looking at points on these two parts of this half circle right here. So my y coordinates are coming from these points. Well, this says that the y coordinate is positive, so it's got to be in this first quadrant, right? Because in the second quadrant, all the y coordinates are negative or below the x-axis. So I need a value of theta that gives me a positive y value of 1/2. But if you draw, remember, there's those few values. Let me put it in red, actually. It's always good to, I'm not going to be super precise, but we have like these 3 values right here. This right here is, it is pi over 6. This one is pi over 4. And this is pi over 3. Those are the points. And the corresponding point, points on in the plane are 1/2 root 3 over 2. This is root 2 over 2, root 2 over 2. And then this corresponds to root 3 over 2, 1/2. And this is the one we want right here. Look at this, the y coordinate of this point is 1/2. Well, that's what we have up here. That's what we're interested in. So this implies that the theta value we're interested in is pi over 6. So what that means then is that sine inverse of 1/2 is equal to pi over 6. So there's 2 other parts. I won't go through them. They're pretty much the same. And I'll leave it to you to go through. So now let's look at the cosine function, the inverse of that. It's going to be almost the same. So the idea is, again, we have this trig function defined on all of R. If you look at the graph, if you use the fact that it's a periodic function, you can see that it is not injective. It fails very much to be injective. They're given any value between 1 and -1. There are infinitely many numbers that get mapped to that by the cosine function. But if we restrict our function to a certain domain, then we do get an injective function. So let's look at the graph of cosine. So we have cosine, it looks like this, and as you can see, it does not pass the horizontal line test, and it fails in many ways. But if you look at the trig function cosine of x restricted to 0 to pi, you get this arc right here. You can just isolate it and put it over here, 0 to pi. And it clearly satisfies the horizontal line test. So therefore we have an injective function. Remember, there's there's like three pieces to a function. There's a domain, codomain, and a rule. And they all go into determining whether a given function is injective. So if you change one of those parts, if you change the rule, or if you change the domain, or you change the codomain, it might change whether or not, or it might change invertibility of the function, or injectivity of the function, or the fact that it's a one-to-one. And that's precisely what we see here. If we change, we're not changing the rule of this function, but we're changing the domain, we obtain an injective function. So I won't, yeah, I guess since I have this up, I'll just leave it like this. So we're going to do that. We're going to restrict, we're going to restrict the cosine function to the interval 0 to pi. So the cosine is now a function from 0 to pi into -1, 1. Passes the horizontal line test, so that means it has an inverse. So now the inverse is a function with the domain and codomain switched. So now cosine inverses has domain -1 to 1 and range, or codomain, 0 to pi. And then we can give this the same, this is now just the very definition of an inverse function. We said cosine inverse of x is equal to y, if and only if cosine of y is equal to x. So this gives us a way of computing the inverse function of x, and then we have these same cancellation properties right here. So our similar cancellation properties. And the graph, if we just look at the graph, where to go? The graph will be, so if you draw, oops. So we have this line right here, it's the line y is equal to x, and you're going to reflect the graph of cosine x on this interval over that line to get the graph of the inverse function. And when you do that, you get this right here. This is the graph of the inverse function. It's cancellation properties. So let's look at an example. So this is example 4. And we'll do part A. So we're asked to compute cosine inverse of 3/2. We want to know what that is, so we'll call this theta. And the question is, what's theta? So this makes sense. It makes sense to ask what theta is, or it makes sense to ask what cosine inverse of this number is, because cosine √3/2 is less than, or it's between -1 and 1. So this makes sense. It's a sensible question to ask. So let's draw our unit circle. That's going to help us. Well, first of all, let's do what we did in the other example. We're going to apply cosine to both sides. So we're going to √3/2 is equal to cosine theta. So cosine inverse of √3/2 is equal to theta if and only if this holds. Remember, that's the definition of an inverse function applied to cosine. So it sort of simplifies the question a little bit. because then we can go to our unit circle and just ask what theta value or what angle roughly corresponds to this x coordinate. Because remember that cosine gives you the x coordinate. It's like a projection. So we'll draw our unit circle. So now in this case, we're looking at like arc lengths roughly, or angles corresponding to 0 to pi. So that means we're going to be looking at this part of the circle. So this will be 1, 0. This will be -1, 0. So we're just looking at both this like top half of the circle. So you're going to be given a theta, and it's going to determine a point on the top half of the circle, and then we're given the x coordinate of that point, so we want to find the angle corresponding to it. So we don't have to draw the whole circle because we can observe that this value right here is positive. So it's going to correspond to something in the first quadrant. If it were negative, then you would have to look at the second quadrant, and your angles might be, or your arc lengths or whatever, might be a little different. So really we just have those three that I drew. I'll draw again. It's always good to do that, just to memorize. It helps you memorize these values. We have these three particular points on the graph. So this was on the circle that we should know. So this was pi over 3. This is pi over 4. And this is pi over 6. This one, so yeah, this corresponded to root 3. Sorry, no. This corresponded to 1/2 root 3 over 2. This corresponds to root 2 over 2, root 2 over 2, and then this one corresponds to root 3 over 2, 1/2. And so clearly this is going to be the theta we're going to be interested in, because the x coordinate corresponding to this number is root 3 over 2. So from this we can conclude that theta is equal to pi over 6. So that means cosine inverse of root 3 over 2 is equal to pi over 6. And then the last one we're going to look at is the inverse tan function. So let me pull the book up. So again, if you look at the graph of tangent, it's clearly doesn't satisfy the horizontal line test, and this is because the function is periodic. But if we restrict the function to a certain interval, we get an invertible or injective function. We change one of the three pieces of the function to obtain an invertible function. So the inverse function is going to be tan inverse. The domain of it is going to be all of R, and the range is going to be between -pi over 2 and pi over 2. Notice we have to use parentheses, not square brackets, because these are points where tangent is not defined. Remember, it has those asymptotes. It has asymptotes at those points, vertical asymptotes. And we have the same cancellation properties. And if we look at the graph of tan x, we're basically looking at this part of the graph. When we restrict the domain of -pi over 2 to pi over 2, we're just looking at this piece, and if you reflect it, you'll get the graph of the inverse function. So that's what the graph of the inverse function looks like right there. Let's do example 6 quickly, and then we'll call it a day. So this is going to be example. Example 6. So we want to know tan inverse of 1 is equal to some number theta, and remember theta has to be between negative pi over 2 to pi over 2. And the question is what's theta? What is theta? So again, just apply tan to both sides. We get 1 is equal to tan theta. And let me just copy the unit circle so I don't have to draw it again. But I encourage you to just draw it. Definitely draw it. I just want to save time, because if you just keep doing this stuff over and over, remember what I said in that one video, doing mathematics is not, or being successful at math is not about being brilliant. It's just about doing the same thing a number of times and getting used to these things and comfortable with these things. It's not about being particularly brilliant or anything. And I'm a testament to that, because when I started out, I was not brilliant at all. I was very terrible at mathematics, actually. So what the heck? Okay, let's see if this works. Okay, so we want to, so we're looking between, actually I should have done the other one, because, okay, I should do the other one because the domain is this. Notice that notice that the range is almost like, the range is similar to the range of sine. The only difference is that you can't include those negative pi over 2 and pi over 2. So I should really be using this unit circle right here. This would be more helpful. Let's see. Actually, I didn't want that. Okay, so we're looking between negative pi over, I don't know why I put the pi over 2 there. Oh, screwed things up a little bit. I don't know why I did that. Anyways, we're looking at a value of theta between negative pi over 2 and pi over 2, not excluding those 2 points. So those correspond to points on this part of the circle right here. So notice we have positive 1. So remember that tangent is a ratio of the y coordinate to the x coordinate. So in this quadrant, the fourth quadrant, the x coordinate is positive, the y coordinate is negative. So any ratio of those two numbers will be negative. So, but we are dealing with a positive number. So that means that the point that we're interested in is in the first quadrant, because that's where ratios of y to the x coordinate is positive. So we're just looking in the first quadrant. Now, again, if, as I said, pointed out in the other one, if this were a negative one, that would mean that we have to look at in the fourth quadrant. So we want the ratio of the y coordinate and the x coordinate to be 1. So this says right here, so whatever theta is, it says that theta corresponds to some point xy, and it says that x over y is equal to 1. Well, that's the case if and only if y is equal to x. So we want to look at a point where on the unit circle where y is equal to x. The x coordinate and the y coordinate are the same. Well, that's pretty easy to spot. It's going to be this one right here, right? The x and the y coordinate are the same. So that implies that theta is equal to pi over 4. And hence, tan inverse of 1 is equal to pi over 4. Okay. So there's a couple other parts to this, but I won't bother going through them. I encourage you to go through them. There's a part B, I would do that. Don't even worry about part C. It's kind of stupid. You have to use a calculator, and I don't really care for calculators. So I don't expect you to use use a calculator to do these problems. So that's all for now. This concludes chapter 5, and now we're gonna have sometime next week a test on chapters 3 and 5. Although I'll make an announcement, so you don't have to worry about that too much. I'll make an announcement with more details. And if I forget, just let me know. I will. If I forget to make an announcement, just let me know. Remind me to. So that's all for this lecture.